Hello, welcome to this new lecture. In the previous lectures, we introduced and discussed the properties of regularized regression, lasso, ridge, elastic net, and in this lecture, I will give a concrete example of how to implement it in R using the public health data that we have been um, using throughout the semester. Okay, so this is the code that we have been working so far. We talked about the predictors we have. We went over everything. That's part of the previous lectures. Now, today we will use the GLM net library. Okay, so let's go over the GLM net library. So if we want to fit a single for a single lambda, then we can use the glmnet.fit function. But we don't want to do that because we don't know what's the optimum level of regularization, right? So we'll use the cv-glmnet. For the cross-validation error, we have options here. The mean squared error, the deviance. The deviance is the log of the negative 2 times the log of the likelihood, which in the linear regression case boils down to the MSE. So for linear regression, deviance and MSE are essentially the same. Class is for classification problems, which we are not dealing with here. AUC, area under the curve, is also for classification problems. And then we have mean absolute error, which is obvious from the name, the mean of the, so it's the L1 norm of the residual, whereas the MSE is the L2 norm, okay? And there's not really a right or wrong whether you should use MSE or MAE, and typically they give similar results. And if we do not specify it, it's the default, which for regression, linear regression, is MSE. We can select the number of folds. If we don't specify it, it's 10. The default is the Gaussian family. which is for us linear regression. This is the elastic net problem, where we have a lambda and we have an alpha. The alpha determines whether we are close to ridge or lasso. So for alpha 0, we are doing ridge regression. For alpha equal 1, it's lasso. So alpha equal 1 is lasso. So CV lasso. CV ridge. CV ElNet. Okay. Now we also have to, we don't have to, but um, in R you don't have to give the range of lambdas. It internally can figure out a lower and upper bound within which it will split the interval and calculate the cross-validation curve. But if you are using a different programming language, such as Python, it is possible that the GLMNet implementation may not come equipped with this feature, and you have to provide the range of lambdas. And it's a common question: how do you determine that? So this is something we'll do. Here we don't have to, but I will just go through the process in case you are working with a language that does not internally determine it. The way to do it is essentially you want to find an interval that captures the U shape. So you don't want to be too much to the far left or too much to the far right, but where those boundaries are determined by the problem, and so that's why we can't say specifically, oh, go from 1 to 10. But we experiment with it, so we just say, okay, let's see, LNB, say, um, oh, by the way, this interval will be different for lasso ridge and elastic net. So let's just start for lasso. Okay, so I just chose this interval 0.1 to 1, and you see at the end of the interval there are 0 variables selected. At the far right, at the far left 24, P is 127, so that means that this interval is too much to the right. We are too much regularizing. So let's just go to start at a smaller place. Now it's okay. So now by looking at this, you see we're capturing the interval. P is 127. So we even, oh, but N is 71. So um, if we don't use it, then this is the interval internally selected. So this is how you select the interval in case you need it, but in R we don't need it. So just leave it at that. Bridge. Then for so now that we ran this again, the cross violation curve changed slightly. So let's just run this again. You see the minimum is at degrees 11. We run it again. It's now a little bit more than 11 and the curve has changed. We do it again, changed again. It's more or less looks the same. It more or less points to the same minimum, but it changes from each time we run it. It's the reason is that the default is tenfold cross validation, and for each time cross validation is performed, there is a shuffling going on, and that shuffling is random, and that variation that we see from sample to sample is because of that um, variability. Now, if we set the seed, obviously, all of us going to get the same um, variability. So, if we run the same code with the same seed, regardless of which computer, you get the same thing. Now, the only cross-validation that there is no variability involved, because even when you shuffle it, essentially the only cross-validation that regardless of the shuffling, um, you get the same result is leave one out cross-validation. So if you set enfold, enfold, forgot, n, then this is the curve we get, and if you run it again, you get the same result. Okay. So n-fold cross-validation is the most attractive one because it has the smallest variance and the smallest bias, despite what the book says. It has the smallest variance, it has the smallest bias. And just as a um, side note, let me show you something. Actually, never mind that. That's a little bit too technical. So, but essentially, what I want the take-home message is that if we run out trust validation, that is desirable. But if it's too much, then anything like tenfold would work, and too much is just depends on the context. So uh, you just have to see for the application. But I mean, here we can run it, so we let it run. Okay. This CV lasso object has different attributes. These are the lambdas that are automatically used. This is the value of the cross validation. So 39th. The 39th, which is the 39th? This is the index of the lambda that leads to the smallest cross validation error. And what is that lambda? It's this one. So at point 1, it is cross validation error is the smallest. And what is the log of it? Negative 2.25, which refers to this point here. And there's another way to get the minimum lambda. It's the same. Okay, so this is the lambda we will use to fit our lasso. Okay, so we run the cross validation to select the proper model complexity, and then we find the model that has the same complexity. For that, we need the GLMNet, Y, alpha, another thing I wanted to show you about the CVGLMNet is the solution path, which looks very interesting. So how do we get the solution path? So actually, instead of using the lambda min, let's um, fit the model for this whole lambdas so that we can plot the solution path and see if there's a obvious break. Okay. Very interesting. Now this one shows the L1 norm of so we've seen the coefficients versus the L1 norm of the estimate. And here we see the degrees of freedom. We know that the minimum cross-validation error happens, I guess, somewhere here. Here's the problem. That's the problem. It's not a problem, but if we want to see this in terms of lambda, then this is what we're going to do. Okay. So the minimum is around, if you remember, CV lasso lambda min 0.1, degrees of freedom slightly higher than 21. Let's see if we can get also degrees of freedom. I think there's a way. Number of zeros, I guess. So n0 tells us essentially the degrees of freedom for the corresponding lambda. So, but which of these indexes refers to the smallest cross-validation error? Which mean CV lasso 639. So what is it? The lasso 22, which makes sense. So this is 22, this is 24, 20, this is 22. Okay, so 22 variables are selected out of 127, and in a minute we will look at them, but first I want to get back to the solution path. So this is the minimum, and okay. This is log. The log was negative 2.25. And the negative 2.25 is somewhere here. So the variables that are selected up to here, which means this black one, this one, these ones are considered to be associated with the response, and everything else that shows up later, we don't consider that to be associated with the response. Okay, and then let's look at the lasso fit object. See which is equal to CV So these are the intercepts, but we only want one of them, the one that leads to the smallest cross-validation error, and also we want the estimated coefficients, beta. So this is a matrix, right? This beta is a matrix where each column, so let's look at dimensionality. So 127 rows, 100 columns. Where does the 100 come from? The 100 is a default um, of R. So let's go back to the GLMNet package. Where are we? Okay, so it doesn't say it, but you see this its own sequence. The default is that to choose a sequence of 100 lambdas. You can change that, but that's where the 100 comes here. And 127 is the number of features we have. So each column corresponds to a specific lambda. And we are only interested in one of the lambdas, so we pick the column that refers to that lambda. So all the rows, that column. This will be our beta hat lasso, and this will be our A0 hat lasso. So what is the intercept? It's around 6, okay. And this is our beta hat lasso. Let's see which variable was selected. Church is selected, age is selected, years residence in the USA, marine, general health, IPAC, meal planning, food shopping, neighborhood, variables, alcohol, SNAP, political views, adulterative stress. All of these are selected. Oh, actually not all of them, but you see some of them are 0. But anyway, these are the coefficients. Now we can repeat the same thing exactly for, we can do the same thing for ridge and elastic net. So the degrees of freedom of ridge, what are the degrees of freedom of ridge? It will be all the same. It will be 127. Yes, we'll select all of them. That's what ridge is. But I mean, I just leave it there. Now, for ridge, it's very interesting. There is no minimum. It's very interesting. So when I see this, um, that's why I want you guys to plot the cross validation curves. When I see this, I suspect that the sequence chosen by GLMNet, um, the internal routine is not doing what it's supposed to do, because the reason is I don't see a U shape. But it might be also that this is how it is. Not all cross validation curves need to have a U shape, but in order to make sure, I create my own sequence, and I start with a sequence point 1 to 10.1. Let's see what I get here. I'm curious. Okay, you see? So we cannot always rely on these default selected um, intervals. As we saw here, for whatever reason, we don't know what's, I mean, we know, you can look into the paper that wrote this CVGLMnet. Actually, let me show you the paper. So if you're interested, for example, to see what's going on in this package, you should read this paper. I'm not saying you need to, but just so you know that there's typically a paper associated with any of these packages, and if you're curious, you can get to about what's in the happening inside of it, then we can always refer to them. And this is in the Journal of Statistical Software, so it's pretty accessible. It's meant to be for an applied audience. Okay, but anyway, this is outside the scope, but we see that this interval selected was not really optimal. So what I do is, I see it goes up here, so I start from 0 actually. Log of 0 is 1, so I start from 1, and then I go to, well, wait a second. Log of 1 is 0, okay, yes. Log of 10 is not, okay, so it's the log of the exponential, so it's ln actually. Okay. So this is actually exp1. exp1, so it's 2.7, and then I go from exp1 to, okay, now I know what I'm going to do. I'm going to exp a sequence, and I go from 1 to 2, and I create 30 of them. I see. Yeah, we don't need this. We don't need sequence. Got it. Let's just do this. Okay. Okay. So we're capturing the minimum, and this is the solution path. Okay. Now let's do the same thing for elastic net. What is the degree of freedom for ridge? 126. CV ElNet. So the first thing I want to see if the internally selected interval makes sense. Makes sense, so I don't need to give it manually. Okay, let's see what the DF, ElNet, 25, DF, lasso. So it's nice. These two are not very different from each other. Okay, this is really interesting. Now we have a. Wait a second. I'm really curious about this the log of the CV ElNet lambda min. It's negative 1.5, so it's around here. Anything that shows up, any variable that shows up after this is not significant for us. Which is a little surprising. Ah, okay. It's because this alpha here is 1. So you see when you copy paste, you can make these mistakes. Alright, so let's run this again. Okay, so this negative 1.5. Okay, now it makes more sense. Great. So now you have learned how to use these the GLMNet package to apply lasso, ridge, elastic net for variable selection, to do model assessment, to select the proper level of model complexity so that the test error is as small as possible, the estimated test error. And the next thing for us is to try to summarize these results and put them next to each other, because at the moment we have a multiplicity of models that fit our data pretty well. We have Ridge, we have Elasticnet, we have Lasso, and in the previous lectures we saw how to use the forward stepwise method, the backward stepwise method, and the hybrid version. And even though that they may have a significant overlap in terms of the selected variables, um, they are telling different stories, and in order to um, have a better view, we need to um, plot them, visualize them side by side on top of each other, and see, um, essentially take it from there. Okay, at this point we just learned how to get the estimates. Now you have the next thing is for us to put it all together. And that's the subject of the next lecture.